Okay, so good morning, everybody. My name is José Luis Vazquez. I am a member of the data department at European XFEL. And is the microphone working? Is the mic working? Okay. The point of the talk is to explain the challenges we have when we deal with data at European XFEL and how HDF is helping us to deal with these challenges. So XFEL, the previous colleague did a very good explanation, but basically it is a huge microscope. We use X-rays to look into matter at a very small scale. And basically this is a footprint of the installation. Let's try it.
Doesn't work. I think we have to change.
The other one?
Yeah. Better?
No?
No? Yeah.
Yeah.
So there is a tunnel, and the purpose of the tunnel is to accelerate electrons. The electrons come from the... Now this thing is not working. The pointer here. Okay. The electrons come along the tunnel. At some point, they reach this area. This area is called undulator. And when they go through the undulator, they generate X-rays. And the X-rays end up here in these lines. Here is where the experiments are, and it's where the science is being made. And maybe the first thing we can do about HDF is that it allows us to provide a common data format across all the instruments. All the instruments use HDF in the same way. There's not a different format for each of the instruments. The characteristics of the data is that we generate huge volumes of data, and the data is generated very fast. And that is a problem. You can see here, this is a plot of how the data stored at the XFEL evolve over time. You can see now we are storing about 135 petabytes of raw data. This is only the raw data. So we cannot keep up storing data just by adding more disks. You have to draw the line at some point and try to find another techniques of saving storage space. And also the fact that the data is being generated very fast is a challenge because it means that you need hardware and software that can keep up with it. Okay. So you can imagine a facility like that has a lot of machinery, a lot of hardware that needs to be controlled. The control software that we use is called Carabo. It was built from scratch in-house. It is very flexible, very modular. And basically it is made, you can see here a block diagram of it. It is made up of devices. A device is a piece of software that either talks to a piece of hardware and provides an interface to it, or it creates another task like, for example, calibration. You can write a device that does some calibration. And all the devices talk to each other. And there is a message broker here that is in charge of distributing messages across the system. And a key part of this is the Carabo hash. The Carabo hash is the structure that Carabo uses to store data and also to transfer data from one device to another. This is just an explanation of what the Carabo is because it will become handy later on in the presentation. Hash, maybe it's a bit misleading. A Carabo hash is basically a key value container, and the value can be pretty much everything. It can be an integer, an array, you name it. It can even be another hash, which means that at the end you can create a tree-like structure in memory in your device. And also you can attach attributes to the objects in the hash. Just to give you a bit of a feeling of how this works, you can see a Python example here. So I am creating my hash. This is my keywords. These are my values, string or a list of integers, whatever you want to do it. So now I can create another hash, I create a dictionary of attributes, I create another hash, and I can add this hash as an element of the first one just by calling this function here. I can say this is my key, this is my value, the value is the other hash, these are my attributes. And of course, you can access the data just in the same way you access data in a dictionary in Python. And something that is very handy is that if you want to access an object of a hash, which is an object of another hash, and so on, you don't have to go layer by layer until you reach the object you want. You can concatenate all the keywords using dots. You can see it here, and then you reach your object. So here I'm saying, give me the object language, which is in the hash API. I don't have to do 2 calls to reach to this object. So it is very handy. This is a screenshot of what Corabo looks in real life. What you can see on this is the Corabo installation for one of the instruments. Here on the left, you can see all of the devices that make up the system. They are organized in a hierarchical way in a tree. And you can do things like click on one of them, and then here on the right, you can see all the properties that make up the configuration of the device. You can even do things like click on one button here and send a command to the device. So in principle, you can control the instrument this way, but you can see, in here I have like hundreds of devices, each one of them with several hundreds of properties. Is not very user-friendly, let's say. So what Corabo provides is a way of creating what we call a scene. And in this scene, basically, you can choose which properties of which devices are interesting for you. You put everything together in a nice graphical user interface, and it is here at your disposal. So this is the main scene for one of the instruments. You can see, for example, this is the image in real time of the main detector. You can see the state of the optics of the hatch. All sorts of information that is useful to you, you can put in the scene. And the interface is a lot more friendly than just going by the list of devices, selecting one, choosing properties, etc. Now, when it comes from data generation, where does data come from? And the main culprit is the big detectors. They are big and they generate data very fast. We can see here, this is from a detector. You can see this is the CCD. It's a square 1 megapixel CCD. And you can see that it is not continuous. It is made up of small modules. We have another devices which are maybe not so big, but who have many more of them. We have auxiliary data, which is not strictly speaking scientific data, but it is data that you need to understand the scientific data. So at some point, it needs to be saved too. So you can see many sorts of data, many sources, a lot of data generated very fast. The third point is it's like big data in a sense. You have volume, you have velocity, and you have also a variety of data because the data acquisition system has to deal with many different formats. So for instance, the big detectors send data in a format which is called XDF. The auxiliary data is sent in a format proprietary to Corabo, which basically means in a hash. And because it is a hash, you can give it pretty much any shape you want. The DAG here is responsible with the help of Corabo HDF5, which is a library that we developed. It is responsible to gather all those data and make sense of it and save this data in raw format in HDF format. After that, you can do many things like apply calibration to the raw data, and you can generate process data in HDF format as well. So even before we get to saving the data on disk, there are many things we can do to save disk space, which I will talk about at the end of the presentation if I have time. But when it comes to save the data, what we use basically is HDF compression and chunking. There were a few tests being done in the past, even before I joined, where the people did several things like using ZDIF and HDF5, but they didn't prove efficient enough for purposes. So we ended up with compression and chunking, which is at the moment working pretty well, I should say. And the way this works, you can see here on the right, this is basically the XDF format for the big detectors. And the format is, in a nutshell, it's an array of 352 images. But because of the way the bin is structured, it might be the case, and it usually is, that you don't have an image for each of these 352 arrays. Many of them are blank. So there's no need of saving them. So basically, by chunking along the image of the axis of the images, you can choose to save only the chunks for which there is an image with actual information. And that allows us to save a lot of data. This is a plot of the set that we've saved. We only care about the green line here. The other ones are different techniques which have nothing to do with this presentation. So you can see that since we started doing this, in more or less 1.5 years, we have not saved more or less 12 petabytes of data. So it is a big save. So this is when it comes to reducing the amount of data that needs to be saved. But what happens, what do we do to keep up with the speed of data production? And this is where the data acquisition system comes into play. And basically what we do is parallelizing the data storing. So by having several processes, each one of them saving one HDF file, we are able to, let's say, multitask and parallelize data acquisition. You can see this is a fairly simple schema of the data acquisition system. The key component here is the data aggregator. The data aggregator is a robot device that listens to one of many sources of data, gather all the data, packs all the data, and the output is an HDF file. So actually, it says detectors here, but you remember I spoke, the Egypt detector is made up of modules. So usually you have a one-to-one correspondence between one detector module and one data aggregator. So in the case of the Egypt detector, you have 16 data aggregators gathering data from the detector and writing the data in parallel in different HDF files. And the beauty of that is that HDF provides a coherent way of storing data in separate files. You can have data aggregators that listen to slow sources of data, for instance, or auxiliary data, and they can listen to many sources of data. And the system is scalable in the sense that if you find out that one aggregator is overloaded because it is gathering too much information, you can split the data sources into data aggregators, or 3, or as many as you need. The system is scalable in that sense. This screenshot is from last week. I believe it was from Tuesday, and it gives you a sense of the speeds we achieve when saving data to storage. You can see at some points we reach almost 20 gigabytes per second storing to from the data acquisition system to the online storage, which is pretty fast. So what is Carabo HDF5? It is a library that sits between the hash and the HDF5 standard API library. And basically what it does is mapping hash objects. You remember the hash is a key value container, and its value can be data or can be another hash. So Carabo HDF5 maps those objects to HDF objects. So there's a pretty much natural mapping between a hash to a group. A value can be mapped to a dataset. And also, you can even map the attributes in the hash to attributes in the objects of the dataset. So to give a bit of a more visual way of how this works, this is a screenshot of the properties of a device. This actually is a test device we use, and it has several sources of data, and it is random data. So you have one source data of random floating point numbers, one source of integer numbers, and so on. Okay, so when we acquire this data in the data acquisition system, the data travels in a hash, and if you dump the hash, you get something like this. You can see there's a mapping. You can see a node here. It has a hash inside without keyword and a value, which maps to this guy here. You have a float property that maps to this float property, and so on. So this is what travels across to the data acquisition system. The data acquisition system picks that up and saves in HDF. And if you open this HDF file in this actual is Visual Code, you can see there is a mapping between the data sets in this group and the properties in the device here. So that is the task of Karabo HDF, provide an interface that allows us to map from the hash, which is the de facto standard to saving and transporting information in Karabo, to HDF. How much time do I have? 5 minutes. Okay, I said before that there are a few things that we can do even before we get to the point where we have to save data on disk. And maybe I should explain how the bin is made up. The bin is not continuous. You can see it is made up of trains, and each train is made up of pulses. It's a bit like a machine gun. You press the trigger, you get a burst, you wait a few seconds, you press the trigger again. So each train is like a burst, each pulse is like a bullet. The pulses are very short, and you can have up to 2,700 pulses in a train, which means that you can have data up to 4.5 megahertz. But the thing is that sometimes you don't have all of those pulses. There are patterns, and you can have one each 2 pulses, one each 3 pulses, things like that, which means that for most of those pulses, there will be no X-rays. So you can actually figure out for which pulses there's no X-rays in this XDTF data format I talked about before. And for those pulses, you can discard the image. This is related to what I explained before about the data chunking. Something you can do too is you can have experiments that, for instance, you have the beam coming to a sample, and then you have a laser going like this to the sample. And the point of the laser is to compress the sample so you can observe it. But the laser is going to be shot for a very short time, maybe one train. So you only need to store that train. You don't need to store anything else. In this whole chain of trains, everything can be discarded except the train for which the laser was on. So you can find out which train is that and store only that train. Another thing that you can do, this is a scheme of the image of an EGIT detector. The EGIT is a detector which is smart enough to figure out which gain it has to apply to each of the pixels of the detector. So for each pixel, there is one of 3 possible gains. But that means that you have to save the gain as well, which means the data pretty much is the double, because for each image, you have the array with the image and the array with the gains. But what happens if you have an experiment, and can be the case with very low illumination? You know the gain is always going to be high for all of the pixels. So there's no point in saving all that. So by not saving the rate of the gains, you reduce the data, the amount of data you have to save in half. Okay? And that's my last slide, I think. Any questions?
Thank you, Hamza. I'm pretty sure there must be a question. Yeah, please. Right, maybe, because the people are in the Zoom.
You distribute your data you want to store around your, how do you call it, data aggregators. Is this right?
Yes.
So each single data aggregator, how much data per second has it to store? So if you only talk about one specific HDF5 file.
In the case of the big detectors, I don't remember the numbers by heart, but I think we have them in this slide. So let's go back. Up to 15 gigabytes per second.
One single?
No, that's for the whole detector.
Okay.
So you can see the detector is made up of modules. Yeah. So for each aggregator, it will be 15 divided by 8. So I don't know. Yeah.
Okay.
Okay. Go.
Yeah. First of all, thank you very much for this great talk. And the question would be, you mentioned that you store, like you distribute your data across multiple HDF5 files.
Mhm.
And what is the procedure then to kind of glue them together back? Thank you.
They are stored in the same place, and basically, since the format is self-described, and you know what there is in each file. In the future, and they will correct me if I'm wrong, there's the idea of providing some sort of entry point in HDF5 file that points you to all the other HDF files, but not at the moment.
I'll maybe add one comment on top. Stefan Hauff, also from European XFEL. So our data analysis group also provides a Python library, which basically does all the gluing. The data format Jose showed is pretty technical, and our users usually don't need to be exposed to it in that level of detail.
And if I can add, I think we are using also this virtual data set, which comes from HDF5, to construct the full view of the data. So you don't have to deal with the individual files. And that's basically, I think, how we went about making sure that we can write in parallel, very simple way, very reliable, and then still have this advantage of having one view to the users who are actually analyze the data. Of course, there are a lot of caveats which have to be taken into account while creating those data sets, but that's what our people are doing.
Yeah, and I just see Thomas Clover hiding back there in the background, who's one of the main authors of that library. So best person to ask for questions.
Okay, but I think we still have like a few minutes. I mean, there are some comments on the Zoom, which, let me check. Okay, no, this is just the log. We don't see the video. Okay, thank you. So yes, we do have a problem with the camera during the break. This should be fixed, so yeah. But we have another question here from the audience.
Thanks. So I have a question about the hash.
Mhm.
Yeah, it seems that it is very similar to like HDF5 model. So the conversion is like possible. How you keep the hash? Usually in memory, or also you store it also in files?
I'm not sure I understand the question. You mean where is the hash stored?
Yes.
The hash is programming structure. It's kept in memory.
Yeah, and like kept in memory and like
Technically,
stand between.
yes. Technically, in C++,
different-
it is like a map in C++.
Yeah. Okay.
Actually, it's implemented in kind of a map way. Yeah.
I can add again that you can serialize the hash, which is in memory, to a file. And then I think there's XML implementation or, yeah. And actually the HDF5 also exists, but it's not used for the direct, apart from the specific library, which we use for, this is not direct mapping of the hash to the HDF5, but this is optimized for the scientific data, that is Caribou HDF5. So you cannot call it directly serializer. It has certain assumption, but there is a representation of serializer which can do that as well.
So, and is there something in hash that you cannot store in HDF5? Like just
One thing I can think of at the moment, sets. You cannot put a set as a value in a hash. Sets. If a C++ set cannot be a value of the hash, for instance. I'm not sure if that was the question. If the question was if there's something we cannot put in a hash, right? Actually, I don't know.
So in principle, we could put everything in because it serializes to an XML format, which is a string. So all elements do. What we have, which is out there, which we don't store in HDF5, I should say usually. Caribou supports tables, which are basically is a vector of hashes which all have the same schema. We use those mainly for configuration purposes, and then kind of splitting this hierarchy up yet into HDF5 so far hasn't become necessary. But in the rest of the data types are on either plain old data types, so that is straightforward, or arrays. And Yeah, arrays is the main thing for the large data because there we can chunk along 1 or 2 dimensions and then use the flexible writing that Jose presented.
Hey, Shandor Professor, can you just go a bit forward when you had the description of your hash and how you are putting actually later that to HDF5 file? The question is about that in the graphical user interface, you had all the numbers and also the units. So can you just simply describe how you are storing the units also to the actual data values?
Go back a few slides.
Yeah, a few more.
Yeah.
No, forward. We are getting there. Here it is. So if you just go back to, then we see, for example, the float property, it's degrees Celsius, 215. And now if you go forward to, yeah, right here, then we can see that the float property is indeed 250 as a float. So can you say, where is the unit?
Oh, in this case, there's no unit. This is at this device, as I said, but you can apply units as well to the properties, but not in this case. I mean,
Their attributes on the data set in the end.
Yeah, so each property can be accompanied by attributes, and that could be, for example, unit. Okay, so thank you very much again to the speaker and to interesting questions.